Hey there, it's Danny B from Danny B Tutoring. I like this problem. It's out of this world. It's kind of fun, right? So we found ourselves on a distant planet, right? And we need to figure out the mass of this planet. All right, so without giving away the answer, I'm going to show you how to do a problem like this. So you can see you've got that blue planet right there, and it's got a radius r. If we blow up that little red square into the big square, we find ourselves standing on the planet holding a purple ball, right? And if we were to drop the purple ball, it would accelerate. Now, on this particular planet in the problem, it would accelerate at 6.85 meters per second squared. Here on Earth, it would accelerate at 9.8 meters per second squared. Okay, but this is a different planet that we're on. So here's how we're going to do this problem. Think about dropping the ball. If you drop the ball, there's a force on the ball. That would be the force of gravity pulling the ball downward towards the planet. But as long as there's no air resistance to worry about, that is the only force acting on the ball once we let go of the ball. And so that means that is also the net force, which will accelerate the ball. So that brings us to our equation over here. We have the universal gravitation, that's big G times m1, mass of the planet, times m2, mass of the ball, divided by r squared. R would be the separation between the planet and the ball. And since we're on the surface of the planet, and the planet's large, that is the same as the radius of the planet. Okay, so that's the universal gravitation equation. Now we're setting that equal to mass times acceleration because the net force is equal to the mass times the acceleration. Now, which mass is accelerating? It would be the mass of the ball. So we can eliminate m2 from that equation. We know the acceleration of the ball because they gave it to us in the problem. We know the radius of the planet. They gave it to us in the problem. And you should also know the large value of G, 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. Right? So with a little algebraic manipulation, you can solve for the mass of the planet, m1. We would have to multiply both sides by r squared. So we would have, let's see here, G times m1 is equal to r squared times a. Okay, and then to solve for m1 from there, we would just divide off G on both sides of the equation. So m1 is equal to r squared times a divided by big G. All right, I hope that helps.